This week we'll be looking at neural machine translation, or NMT. You'll learn about the data and machine learning models used for NMT systems and train and evaluate your own translation system in the tutorial. This video will provide a high-level overview of NMT, and the follow-up video will dive into the technical details of the models used for NMT. But before we get into the details of how to solve this problem, we should first understand what exactly the problem is. First, we should understand the general class of problems translation falls under. Sequence transduction is a broad category of problems, all of which involve taking some input sequence, which can be any length, and converting it to an output sequence, which can also be any length. Most language tasks can be phrased in terms of sequence transduction, including speech to text, text to speech, and of course machine translation. The machine learning models we'll look at can be applied to almost any sequence transduction task. Machine translation involves taking a sequence of words, or sometimes characters or subword tokens, in a source language, and converting it to a possibly different length sequence in a target language, while preserving the underlying meaning. The most famous example of a machine translation system would probably be Google Translate. This week we'll learn about the model that's used by Google Translate and train a very simplified version of this model. However, Google's model uses a fair few extra tricks that we won't get into. Google Translate supports 109 languages, and it actually handles translation between these languages, all with the same model. However, there are closer to 7,000 known living languages, so there's still a long way to go. Not all languages have written forms, and most of the languages not present on Google Translate have limited amounts of data. This doesn't mean that it's impossible to create a translation system for these languages. In fact, we'll make a translation system for one of these languages in the tutorial. However, because Google Translate handles all languages with the same model, adding too many tasks with limited data can reduce the performance on all tasks. In this course, we'll use parallel sentence pairs as data points. These are basically a collection of sentences in the source languages and their corresponding sentences in the target language. When using the trained model for translation, however, we only have access to the source sentences. There are tricks you can use to improve translation quality when you have fewer data points, but generally using neural techniques you won't start to see reasonable results until you're using tens or more likely hundreds of thousands of sentence pairs. This can be a barrier to creating translation systems for certain languages. There are a good few sources for parallel sentence pairs. Flashcard-style data used by human language learners can be good for training simple practical systems. European parliamentary data provides parallel sentences across many European languages, and the WMT datasets released each year as part of the workshop on machine translation provide popular benchmarking datasets and are available within TensorFlow's built-in datasets. Regardless of where you get your data from, there will be biases from that data that carry through to your results, and it's important to consider whether your dataset will give reasonable biases given the intended use cases for your translation system. For example, a system trained on European parliamentary data will likely be better at translating political discussion than it will at practical sentences for tourists visiting a country. Within this field, it's also important to realize that many benchmarking datasets, and particularly those created before 2015, have a large amount of overlap between training and test sets. So if you're using these datasets, you may achieve an overly optimistic test performance. There are also biases inherent to datasets, not necessarily because the data was collected in a biased way, but as a result of systemic biases in the culture from which the data was collected. For instance, for a long time, Google Translate would infer gender biases from data when translating from non-gendered languages into gendered ones. Often, the easiest way to handle these issues from a technical perspective is just to do so manually. Once we've chosen the data, we need to do some pre-processing. The first step is normally tokenization. This involves taking a sequence of characters and converting it into a sequence of pieces called tokens. The simplest approach to tokenization is just to split the sequence of characters about the spaces and throw away punctuation, as in the first example. So the sentence, "We had coffee, cheese, and grapes," becomes 6 tokens, each representing one word, and the commas are just discarded. This approach, which is what we'll use in this course, works alright for languages like English, though there are a few cases where it fails. There are more powerful tokenization algorithms out there which are used by state-of-the-art models, that generally look at using subword tokens rather than full word tokens. These algorithms can handle languages that don't use spaces, such as Chinese, and can sometimes help the model to piece together meanings for words that aren't seen in training. Now, I said before that we want to convert a sequence of words into another sequence of words, but neural networks don't do so well with pure text. We actually need to feed in arrays of numbers, and our output will also be arrays of numbers. So we need to figure out how to represent our words as an array of numbers. There are a few ways to do this. The easiest is to use something like a one-hot encoding, where each word is represented as a sparse vector, where each element represents one of the words known in the language. All elements are 0 except for the one representing the current word we're looking at. While one-hot encodings are simple and easy to understand, they're high-dimensional and sparse and don't capture anything about the syntax or semantics of the words. Often we'll instead use word embeddings, which are a lower dimensional, though still high-dimensional, dense vectors, which can be learnt as part of the network. These vectors represent a word's position in some high-dimensional space. Within this space, the word's position contains information both about syntax and semantics. Using this representation can significantly improve results over one-hot encodings, and by using word embeddings learned from large monolingual corpora as a pre-processing step, performance for natural language processing systems can be improved even further. The last step is to evaluate how good our translation system is once it's been trained. To evaluate how good a translation system is, we need to be able to evaluate how good individual translations are. But in practice, quantifying translation quality is actually really difficult. While we have an agreed metric, it's not infallible, so translation evaluation is an open area of research. There are essentially 3 components to a good translation: fluency, adequacy, and overlap. Fluency refers to how fluently the translation reads in the target language. Adequacy relates to how adequately the translation captures the underlying meaning, and overlap refers to the number of words overlapping between the target translation and the predicted translation. So, for instance, if our target sentence is, "Please send this package to Pittsburgh," and our translation is, "Please send this package to Tokyo," the fluency and overlap are both high, but adequacy is low, because the translation will result in a completely incorrect course of action. Additionally, consider the case where there may be more than one valid translation. How do we account for that in a metric of quality? In practice, it's difficult to automatically evaluate how good a translation is, particularly from an adequacy perspective. The bilingual evaluation understudy, or BLEU score, is currently the most common automatic translation evaluation metric. It's based primarily around looking at overlap between target and predicted translations, and while the exact numbers aren't always super intuitive, using this score to rank systems tends to align with rankings by human evaluators pretty well. Now, the details of this aren't super important, but if you're into the math of neural networks, BLEU score isn't differentiable, which means that we can't use it for network training. Instead, we just use a more common differentiable loss function in training, and evaluate BLEU score on some test set once training is finished to get an idea of how our network performs compared to others. So just to wrap up, I've tried to summarize the main pipeline for an NMT system. The first step in any machine learning project is to gather and pre-process data and split that data into training and test sets, as well as possibly a validation set. Then we fit the tokenizer on the training set and use this to tokenize the other sets, and we add start and end tokens and padding to each sentence. Once we've finished the pre-processing stage, we can feed the data to the model and predict probabilities of output tokens, then evaluate the performance with the differentiable loss metric. If we're training, we then update the network weights and either continue training or stop. If we're validating, we use the loss to determine whether it's time to stop training, and if we're just using the model for translation or evaluating the model's overall performance, we then carry through with the whole translation and possibly calculate the BLEU score on the test corpus. So that concludes the introduction to NMT. Throughout this video, we've referred to the machine learning model as a sort of black box. The next video will dive more into the details of these models.